This is VO1 RFX, and today on the bench we have an Elenco model F-1000 frequency counter. I've been looking for a frequency counter for quite some time. It's a staple piece of test equipment to have on a workbench, so I've really been trying to find a good deal on one used. This one was an exceptionally good deal, essentially only really being the cost of shipping. Without further ado, let's go ahead and open up the box and see what we have here. All right, now that we've successfully butchered that Canada Post flat rate box, let's go ahead and take a look at the frequency counter. So we have a very aggressive kickstand that definitely still works. It is spring loaded with enough force to probably tear itself apart. That's okay. It's a fairly small unit, actually, in terms of the overall size, which I'm not complaining about because bench space is eventually going to become a little bit of a premium as I begin to acquire more and more test equipment. And on the rear here, we can see that we've got a ground, we have a voltage selection switch, a 10 megahertz output, and then our regular IEC style power plug. And we've got some caution stuff on the back that I suppose we should probably read. Don't remove covers. Refer servicing to qualified personnel. All right, well, I guess that makes me qualified personnel if I ever need to work on it. Thanks for the confidence boost. Okay, so the important part is that it has a 1 amp 250 volt fuse. We'll keep that in mind. And looks like this IEC plug actually has a fuse holder in there. I believe that's what that is. All right, so let's take a look at this Elenco F-1000 frequency counter. Before I power it on and start trying to mess around with it, I want to take a quick look at the manual so that I know what all of these buttons do and I'm not totally lost in this user interface. You may be wondering if this is an original manual or merely just a unlawful and unauthorized reproduction that I may have found on the internet. And while I have absolutely no comments whatsoever about the authenticity or provenance of this manual, if the brand has been slain, the manuals are free reign. That's not my opinion. That's just someone who sounds like me. So the frequency range that this unit operates is from 10 hertz to 1000 megahertz, which is perfect for my use case as I'm not doing any kind of microwave type stuff. So if we're really, I'm just focused on the HF spectrum, as that's pretty much everything that I plan on working on. But it's nice to know that if I'm doing something on 2 meters or 70 centimeters, it's also supported, and possibly even something slightly above that. The unit is fairly new, and new obviously is an extremely relative term in this instance. But for example, it's all solid state. It's not a vacuum tube frequency counter, of course. I think it's kind of just obvious by the sheer size of this that the there's no tubes in this, which is great for me because I am not really at a stage where I'm comfortable working on vacuum tube equipment yet. The most we might be dealing with is 120 volt mains, which we shouldn't downplay the safety aspect of that and the risks involved, but it doesn't sound so bad compared to 800 volts DC coming off of an old Heathkit HP23 power supply. So there are two BNC inputs on the unit. One is for 10 hertz to 100 megahertz, while the other is for 100 megahertz to 1 gigahertz. Though it's worth noting as well that they have very different impedances and voltage ratings. So the A input here on the bottom is rated for 250 volts max, and it has a 1 mega ohm 35 picofarad input, and the top is only rated for 3 volts max, and it's a 50 ohm input. For the display, we have an 8-digit 7-segment style display, as well as a few extra accoutrements for gate, overflow, kilohertz, megahertz, and microseconds indications. Funny enough, it says that it has an optional internal battery, and it can actually be powered from the internal battery. That's interesting, although the first thing that evokes in me is fear that an internal battery was put in there a really long time ago and it's still in there and has corroded. Uh, Gee, I wonder if it'll turn on. Okay, well, if someone put an internal battery in there, they did so a very long time ago. That's probably kind of risky for me to do, but the previous owner did say that the unit was pulled from a working shop, so I'm not actually terribly concerned about the internals and that sort of thing. So I think we will take a brief look inside the unit just to make sure that there's no either damage from shipping or capacitors that are like really obviously grossly in need of replacement. And then we'll go ahead and follow the operation procedures for turning the unit on. All right, so just taking a look at the unit in terms of how disassembly is going to go. It looks like we've got a two-piece sheet metal enclosure where there's a seam right here running along the bottom, and we've got a front panel and a back panel. So hopefully, fingers crossed, um, we either don't have to remove this panel and the guts will all just kind of come out, or if we do, everything's going to come nicely with it. But all the screws are in the back, so we're going to start there. There are, of course, screws for the rubber feet. All four, well, these aren't rubber, these are plastic. Let's try the four screws on the back, see if we can't get lucky with the whole thing sliding out the front or back. As always, we're going to get a little tray for our screws so we don't lose them. All right, I don't think we'll quite be so lucky, but let's see what the situation is here in terms of getting this unit out of the box. So I just took a peek inside, and unfortunately, I'm not going to be able to show it on camera, but I can see that the way the sheet metal seams work, it looks like at least the back rubber feet, probably the front plastic feet as well, do hold this panel onto the rest of the enclosure. So I do think this is the right way in. All right, so the camera just had a brief incident of heat stroke there, probably because of the large incandescent lamp behind it that I'm using as a photo light. All that I've done is just remove the four screws in the back that keep the faceplate on. This little chip here was already there when I opened the unit. I did not see a piece in the box, so I think that it just came like that. Then I removed the two rear rubber feet based on the theory that this little sheet metal panel here, the seam, is probably how we're going to get into this thing. And well, then after that, do you ever think that something's going to be a bad idea, but then you do it anyway? Well, that's what happened with these guys up here. I removed one, and as I was doing it, I was thinking, this thing is seriously like spring loaded, as you can see. So I have a feeling this is probably booby trapped, and if I unscrew those, it's going to be really painful to get them back in. And sure enough, it was really painful. And I noticed that it's actually not necessary to unscrew those to get the unit apart. So I cobbled those back together while the camera was taking a time out in the shade. And looks like we now have access to the unit. So let's go ahead and turn this around. Let's just gently slide this out. It is kind of in its own little caddy of sheet metal, as we can see. So we have the bottom side of the main and possibly only PCB in this unit. Looks really clean. It looks like it's in really good condition. Um, I'm looking around for any signs of well, human activity and also any signs of danger. A couple capacitors that are added to the bottom. Well, sorry, excuse me. Three capacitors and one resistor soldered to the bottom side of the PCB. I don't necessarily expect that those are add-ons after the fact or anything. It's pretty common for little bodge work jobs like that to be done at the factory. So, oh, we've got the power transformer, of course. We have our IEC socket, our BNC, our 10 megahertz BNC output, and then our power switch between 110 and 230 volts. Oh, sorry, 115 and 230. It's all in the same ballpark. So let's flip it over and see what we have on this side. Oh, yeah, here we go. Here's the good stuff. So this is a really nice, clean unit. You can see inside the unit, we only have what appears to be two electrolytic capacitors, although they both look like they're in good condition. Of course, looks aren't everything. We have some kind of integrated circuit. Looks like it's in a 40-pin dip package. It's labeled intersil. The part marking is ICM 7226 BIP S8836. I'm not sure what that is, but I'll probably have a little bit of an interesting rabbit hole looking up what that is. Then we have a couple of Motorola. These look like DIP 14 package ICs. Oh, there's a third electrolytic capacitor here. These are, what are these? MCH 74 HC04A. Okay, so those are the logic series chips, I believe. SN74LS. Yeah, okay, so those are little logic chips. That's all well and good. Got some diodes, some resistors, and lots of use of little board connectors, which is great, keeps it nice and clean. It's hopefully going to make any further disassembly really easy, although we're lucky we won't have to do anymore. I did spot a fourth electrolytic capacitor here. Oh, and a fifth, and let's see, there's some more components hiding here under this piece of shielding, and probably also this piece of shielding. We have a second PCB here for the display, or the front panel, as well as the display by the look of it. You can see there's quite a lot of solder pads here laid out in a way that sort of, to me, looks fairly consistent with what we'd see with about 8 of those 7-segment displays. And we have a nice big connector separating the motherboard, I guess you'd call it, to the display slash interface daughter board. All of the buttons, the push buttons and all that sort of stuff on the front panel are actually connected to the main board by the looks of it. They're all through-hole soldered in on the bottom. Yeah, so looks like the daughter board is just for the 7-segment display, if I'm not mistaken. The BNC connectors are chassis mount, so they go straight through the front panel through some shielding here and here. So yeah, it looks like that little daughter board PCB is just for the 7-segment display. It may contain a driver IC as well, if the driver IC is not this guy here that we were looking at, that 40-pin Intersil ICM 7226BIPL. Without removing some of the shielding, it's going to be a little bit hard to say that we looked at the entirety of the unit, because there are some capacitors hiding in there. I'm not super keen on removing that shielding, only because it requires removing, in order to remove this shielding, we need to remove this shielding. And in order to remove this shielding, we need to do what? Well, it's not quite clear. This lower piece of shielding here has 2 screws here that are on PCB standoffs. These 3 tiny screws here, they're Loctited in, or they've got some kind of adhesive on them. I don't really want to remove those if I don't have to. So I don't really want to damage it. One thing I'm noticing as well, the shielding, like, almost bows out in a way that doesn't really look like it's supposed to do that, but who am I to say? I've only seen the inside of this unit for a couple minutes. So what's our attack plan for getting in here to look at the rest of these capacitors? I did a deeper look inside with a flashlight to get in and look at the electrolytics under the RF shielding. I don't really have any concerns about anything in there, so I'm comfortable powering this unit up as is, but I'm going to do it on a dim bulb tester and a variac just to be extra safe. The power consumption maximum listed in the manual is 10 watts. Unfortunately, I don't have exactly a 10-watt bulb. I have something close that's slightly over that. So it's going to provide some protection for any kind of gross shorts that are quite severe, but it's not ideal. So there's a possibility that we might see some activity on the dim bulb that may or may not actually be signs of something bad. The other thing that we're going to do before we power it up, of course, is check the fuses. There's a little bit of conflicting information here about the fuses. The rear panel states that a 1 amp 250 volt fuse should be used no matter what, regardless of whether you're on 115 or 230 volts. The schematic shows a 115 amp excuse me, 115 volt 1 amp fuse and a 230 volt 0.5 amp fuse. The fuse holder says only use a 250 volt fuse. And then the fuse itself, as well as the spare fuse in this little drawer holder, they are both 250 volts at 0.2 amps. So there's quite a discrepancy here. This is 1 amp and this is 0.2 amps, both at 250 volts. So we might have kind of a nuisance blow situation here. I'm going to test both of these, make sure that they're working. However, given that the unit was working originally with the previous owner, I don't necessarily expect this to be a problem unless they put some new fuses in there. I don't really think that would have necessarily happened, but we'll take a look. We'll check the fuses, and if everything's good, we'll bring this up on the dim bulb tester and the Variac. All right, so I've dimmed the lights in the hopes that the camera will be able to pick up the filament of the dim bulb. We have our frequency counter plugged into the dim bulb tester and the dim bulb tester plugged into the Variac. So we're going to start by bringing the Variac up to just about 25 volts. All right, and after giving it several seconds, we have no sights, no smells. So I'm going to move on up slowly to 50 volts. And I'm still not seeing anything so far on either the frequency counter or the dim bulb. And after sitting at 50 volts for a safe amount of time, we're going to move up to around 75. Okay, so at about 75 volts, it's really hard to see on camera, although I can make it out fine in person. We have a single 0 digit showing up on the frequency counter, so that's a good sign considering there's no activity at all from the dim bulb, nor are there any unfortunate sights or sounds. So we're going to bring it up to around about 90 volts. And we're starting to see some digits happening here on the screen. Really hope you can see it because it's glitching out in a way that's terrifying, but also kind of cool. So I'm going to power it up to 110 volts and hopefully, there we go. Yeah, so we're seeing that frequency readout start to stabilize. It's now gating by the looks of that blinking LED, and it's simply just picking up noise, presumably. And it looks like the unit is functioning okay. So I'm going to leave it for just a little while to make sure I didn't get too ahead of myself and something doesn't go bang. And if everything's okay, we're going to take it off of the dim bulb and the Variac and power it back up with the lights on and see if we can test the actual usage of the frequency counter. Okay, so let's take another brief look through the instruction manual, but this time with the unit actually on hand and powered up. And we'll just do a whirlwind sort of tour. We have the hold-in switch, presumably to keep a measurement held on screen. We have the reset switch. When pressed, immediately resets the counter to begin a new measurement. Is usually used in the totalize mode to begin a new measurement. Then we have the gate time switch, which has a table here of frequency resolutions and period resolutions, as well as what gate time is used. So it seems like we're going to be setting our gate time based on what it is that we're trying to measure and with what kind of resolution. And we have the check switch, when pressed, counts the internal 10 megahertz time-based oscillator. So we've been seeing 10 megahertz this entire time on the unit, and that's because the check switch has been depressed the entire time. It's likely the last thing that the previous owner did before they sent the unit off, just to make sure that it was in fact still working. Then we have the A.tot switch for totalizer measurement, and I would presume, based on the fact that this switch and the next few ones down are all prefixed with A dot, they apply to the A input. We also see there's this prefix with B and B there. So then we have our frequency range selection. So we have 2 for the A input and 1 for the B input. So as we can see here, the B input is from 100 megahertz to 1 gigahertz. The A input is from 10 hertz to 100 megahertz. So you're going to be essentially, I guess, selecting which kind of input you're using based on the frequency range, and that in turn determines what input you're going to be using. We have an input attenuator switch. When pressed, the sensitivity of the input signal is attenuated by a factor of 20. I'm fairly certain, though, if you refer back to the specification sheet, the attenuation is only on one output though. Yeah, so it's only on the channel A output here. We have the option of times 1 or times 20. We have the gate indicator, which is this blinking LED that we've been seeing. Um, and then we have an overflow indicator down here. I'm assuming that overflow in this context is the same as it is in computing. So we were measuring a number that was higher than the sort of maximum range for this. We'd see an overflow. And then we have three annunciators, a kilohertz, megahertz, and microsecond annunciator. We can see on the right side of the panel. So it does make me wonder if, given that we're measuring the 10 megahertz internal time-based oscillator, should we be seeing a red LED lit here for megahertz? Or do they not bother rather, to show it when you're not measuring something from the inputs and you're just doing the check? Check mode. So, okay, we already are in check mode. The self-check mode provides a means of verifying proper overall operation of the counter, excluding the input section, time-based accuracy, and time-based dividers used in the period mode. Okay, so it's obviously not a full gamut self-test or anything like that, but that's okay. So the procedure is to power the unit on, press the check switch, and start going through the gate timer. So we've kind of already done that. We're at the 1 second gate time setting, and we can see it's flashing at roughly 1 second. And the display should read 10,000 with 3 zeros after the decimal place, which it does. And if we move down to the 0.1 second gate time selector, the display should read 10,000 with 2 decimal places. And the gate selector should go to 100 milliseconds, which I'm going to take it on good faith that that's 100 milliseconds. And yes, indeed, we do have 10,000 with 2 zeros after the decimal place. And now if we go to 0.01, the LED is probably going to blink so fast, it's just going to look like it's on. Yeah, it kind of just looks like it's flickering, which is fine. I mean, if we're in this gate setting, we know that it's gating really fast. And we see 10,000 with 1 zero after the decimal place, which is what we would expect. Okay, and then the rest of the manual is the calibration procedure. I'm not going to calibrate this because we do require a 10 megahertz signal source to perform that test, and I don't have an accurate 10 megahertz signal source that would be suitable for calibration. So we're not going to do that. And we don't need the schematic, at least not today, or the parts list, thankfully, because everything appears, I do say appears, to work. So the only thing left to do now is to test the unit out with the very crappy signal generator that I do have, which is one of those FG-100 DDS signal generators, I think it is. It only has a maximum output of, or maximum frequency, I should say, of about 500 kilohertz, I think. So it won't make for a particularly interesting test, but we'll at least be able to do some testing of the input section that's not just the internal time-based oscillator. We'll probably be able to answer that question about how these annunciators work, and we'll see how that goes. So let's try that next. Okay, so we have our Craptastic FG-100 DDS function generator, which only goes up to about 500 kilohertz, I think. Certainly under 1 megahertz. And we're going to see if we can get any readings on the frequency counter. Hopefully we do. That would be pretty important. It's worth noting that the unit has only been powered on for maybe 7 minutes or less, and it was powered off for probably 1 to 2 hours. So it'll be interesting to see what the readings are, because I guess this is technically a cold start. The startup requirements for the unit were something like 20 or 25 minutes in 25 degrees Celsius ambient temperature. So if this is indeed a cold start, I'd kind of be interested to see what a cold start actually looks like in terms of accuracy. However, I think it's probably quite likely that the accuracy also deviates with increases in frequency. So if we start out really low here at 1 kilohertz, then it's probably going to be bang on. And then as we raise it, who knows, we may not be able to really actually reach a point where this is inaccurate from a cold start. So let's go ahead and connect up our frequency counter to our signal generator. Got the amplitude all the way down, so I would not expect to see a signal at first once we hit the go button. So based on what we've learned from using the manual, we've got our A input and we're going to be measuring under 10 megahertz. So we're going to want to be on this setting. And well, that answers our question about the annunciator LEDs. So when we're not using the check mode, these LEDs do in fact light up, and I can probably just put it into 100 megahertz. And yeah, that one lights up as well. And the A period, short for A input period, button should make this one light up. Great. Okay. Well, all three of those LEDs are working, so that's an interesting tidbit that we can go ahead and check off our sort of questions and answers list. So let's go ahead and start this at what are we at? 100,000 hertz? Yep. Let's go ahead and start that, and then we're going to bring up the amplitude until we get a reading. And there we go. We have 100 on the dot. There's a little bit of deviation. The other thing is that this is an awful signal generator, so it's kind of hard to tell who's actually wrong in this situation. We have a very crappy signal source, and then we have a function generator that's also cold started. But it's kind of an interesting test case, I think, because certainly the cold start aspect, you know, if we leave this for the remaining, about 10 minutes, 10 and a half minutes left until we've, no, more than that, 15, until we've reached the 25-minute period, then who knows? We'll see what kind of deviations we get after that point, if any. So let's go ahead and stop the frequency counter, and let's just move slightly. Let's increase by 100 hertz and see what happens. And there we go, 100.100. And just off by very slight amount, but it just deviates. But we do get the stable reading that's bang on, 100.100 right there. So that's great. So let's go ahead and keep on trying out some different frequencies. Let's try 150,000, 100, bang on. All right, and we might as well just go big or go home. I think we can go over 500 kilohertz on this thing. So let's try this. Yep, that's fine. So or is it? Yes, it is. Also, we have the gate time to contend with as well. So theoretically, changing the gate time would be, well, in this case, not so helpful. So a faster gate time may not necessarily be advantageous if we're trying to measure this, depending on what the situation is. It seems to do pretty fine at the 1 second gate time for this, but I think we are reaching the actual limit of what this thing is supposed to be putting out. So we've got a good reading there, 550.099. Now, we can go higher, like the interface on this does allow it, but it's a question of whether or not it actually puts out a reliable signal in that range. So I guess we will see. Maybe not. Now, why don't we back it down to the actual stated operating range of, let's do 450, or 450,000 rather, on the dot. See what we get there. 449.999. So that's pretty good. I'm happy with that. Now, of course, we're only testing like the absolute bottom of what this unit is capable of doing. And unfortunately, until I get a signal generator that's not this one, we're not going to be able to truly test the accuracy or the full range of this unit. We could possibly use some radios hooked up with proper attenuation and that sort of thing. We have added the sample output tap to our dummy load, which I did in video number 1, if you haven't seen that. So we could use that just so long as we kind of do the math first and make sure that we're not going to be going too high on the input. But as far as this thing is concerned, I think this unit is doing just fine. And again, it's a cold start. Technically, we won't be at a warm start or warmed up for another 11 minutes by the look of it, according to my stopwatch. And I'm really not sure what the stability on this kind of thing is or the accuracy. So I'm not too worried. I think all in all, this is pretty decent. And well, hey, why don't we try the display hold function while we're at it? Go ahead and come off of self-check into the 10 megahertz setting, and let's put this on, I don't know, 50,000 hertz, and we'll run that, and we'll see, there we are. And so it's fluctuating ever so slightly. So let's see, where's our hold button? Right here, 50. The gate LED has stopped, or it's stayed on rather. So that would seem to imply to me that the frequency's been held. Again, just like on a multimeter, if you hit the hold button, we can probably unplug it. And yeah, so it's obviously essentially in memory at this point, and so that's cool. That's useful. Good to know. Changing the gate at this point just affects the decimal placement, which is interesting, even though the gate time is actually not changing. And if we hit the reset button, this should reset and make a new frequency measurement right away. So if we stop this and then let's move it to 150,000, and we'll plug it back in because that might be helpful. And we make sure that it is running. And then we immediately hit the reset. What do we get? Oh, okay, so the hold is actually latching. So seems like we have to come off of hold, and now we get 150. And so we could hold that again at 150.003. We could reset it to 0, but if the hold switch is still latched, then we're not actually going to take another reading, apparently. Did mention in the manual that the reset was, I think, most useful in the totalize frequency, totalize measurement option. So sure it'll come in handy in that instance. Okay, well, we've answered quite a number of questions about how this unit works, and we've answered one of the biggest questions about whether these annunciator LEDs work. We've got the hold button figured out. We've got the reset button figured out, and a few other things. So that's good. I'm happy. Again, we aren't able to really test the anything but just the bottom end of the frequency range that this is capable of. But I'm pretty happy with what I've seen so far. I think what we'll probably do with this next, aside from just using it in videos when we need to have a frequency counter, is that once I do get a proper signal generator, we'll make another video about doing the calibration on this unit. And I think if we are going to go through the trouble of calibrating it, we might as well replace some of those capacitors that were in the RF shielding area anyways. They kind of like passed my own sort of inspection, in that I didn't think they were risky to have powered on, but I'd kind of rather just replace some of them. So I think maybe we'll do that next once we have a signal generator. We'll do the full test of the entire range of the frequency counter. We'll then replace some of those capacitors, calibrate it, or maybe we'll calibrate it and then replace it, calibrate it again, and see if things changed, if we screwed anything up. But that'll be a future project down the road once we have some more equipment. This is VO1 RFX. Thank you very much for watching as always, and this is what was on my bench today.